All right, here we are at our 4.12 part 2, writing numbers in scientific notation. So in part 1, we were kind of taking our values and creating them in standard form. Today, we're kind of working in reverse and trying to get them into scientific notation. So kind of the sequence on how we do this is we always want to first locate where is this decimal at, because that's going to determine how many times we move that decimal place. So you always want to first find where is our decimal place at. Then you want to move that location, and we talked a little bit about this the other day, where your number is always in between 1 and 10. Now you can be 1, but you can't be 10. And today you're going to see why you can't be 10, but it can be 1. And your value is always going to be in between 1 and 10. So yesterday we saw a lot of like, hey, what happens if you have 7.28 times 10 raised to the, I'm just making this up, a fifth. Notice how this value is in between 1 and 10, that being scientific notation. Then you're always going to follow it up by this times 10. And then we're going to count how many times do we actually move that decimal point over, and that is going to be used for your exponent. And again, in part 1, we moved that decimal over that many times, so it should kind of resonate with that. And then finally, you want to figure out, is this exponent positive versus a negative one? Now, if it's a really, really large number, this is where we see those positive exponents come in. And here's a prime example. 8,600 is going to be rewritten as 8.6 times 10 raised to the, see that where it's a positive 3 there, because we had originally a very big positive number. So this was a big positive number. And so that's why we're going to make our exponent positive. Whereas if you have a really, really small number, something smaller than 1, those are going to have negative exponents. So again, the teeny tiny stuff, things that are really small, are going to include those negative exponents. So this would be a prime example where we start off with a very, very small number. It's really close to 0. And then we create it in this scientific notation by moving the decimal over in between 1 and 10 is that value. And then our times 10 raised to the, we would count this and it would have been moved 3 times. But since it was a really small number, we have this negative value. Okay. And then the only other one is a number that is less than 10, but at least 1, making that exponent to be 0. So for example, these are kind of seen as like, I would say the boring ones because you don't really do much with them. You have 9.52 to start off with. Well, notice how this number is already in between 1 and 10. And so the scientific notation of that is you pretty much just repeat the exact same number times 10 raised to the 0th power. And your Algebra 1 teacher, they talk about what does that mean, anything raised to the 0th power. They talk a little bit more in depth on that. But essentially, we haven't really moved our decimal at all. And so that's why it is still to the 0th power. We didn't move it right or left any. It just stayed as it was. So now let's actually see these in action. So we have example 3. We're asked to write each number in scientific notation. So as we look at A, we always want to first identify, well, where is our decimal at? And so when we look carefully, we have the number 618. Well, 618 is the same thing as saying 618 with the decimal at the end. Now my goal is to try and get this number in between 1 and 10. So in order to do that, I would have to move this decimal over, looks like 2 spots to make that happen. And now I end up with 6.18. And I notice, hey, my number is in between 1 and 10. That's great. I needed that. And then following those steps, I have my times 10 to get it in scientific notation. And again, we moved that decimal over 2 places. So that's why my exponent is 2. Next, I would check, well, is it a positive 2 or a negative 2? Well, since we started with a big number and we brought it down into that scientific notation, that 6.18, we're going to leave this as a positive 2. Okay, you don't even need to write the positive 2. You could just leave it as that. Next, we're going to go ahead and try B. Again, we want to first identify where is our decimal. Well, if we have 3,500,000, our decimal is actually at the end here. And again, we need this number in between 1 and 10. So I'm going to move my decimal over 1, 2, 3, 4, 5. I'm still not in between 1 and 10. I'm at 35 right now. But if I go one more time and I have my decimal there, I now get 3.5, which is in between that 1 and 10. And then from our steps with scientific notation, we have times 10. And then we want to ask ourselves, how many times did we move this decimal? Well, it looks like 1, 2, 3, 4, 5, 6 times, grand total of 6. And since we had a really, really large number, really big number, that would, to start with, that would be a positive 6 for the exponent. Again, if you start with a really big number and you bring it to scientific notation, this guy is going to be positive for that exponent. Now let's take a look over at C. Very similar. We have 56,900,000. We're again starting with a really, really large number, and our decimal place is here at the end. Now again, I need this number to be in between 1 and 10, so I'm going to move my decimal over 1, 2, 3, 4, 5, 6. And I have to go one more 7 times. And so I end up then with 5.69. And I don't have to write all these extra zeros, okay? Because when I do my scientific notation, I can do times 10. And again, we took a really, really large number, brought it down into scientific notation. So that's why our exponent is still positive. Now when we try something like question D. Well, here we actually have a really, really small number. This number 0.0098, that's really tiny. That's really close to 0. And our goal is always to try and make scientific notation in between 1 and 10. So in order to do this, I'm going to need to move my decimal over. Looks like 1, 2, not quite there. That would be 0.9. So I have to go one more to get this value in between 1 and 10. And I ended up with 9.8. That is in between 1 and 10. And it looks like I had to move that decimal over a total of 3 times to accomplish that. So times 10. Now, because I started with a really small number, tiny, close to 0, and I had to move my decimal over to get into scientific notation, this is now where we have that negative pop up. So -3. And that is our scientific notation for those really small guys being brought up into that scientific notation. Now moving on to E. Again, we see a really, really small number here. It's really close to 0. We have something small, and we're trying to bring it up or scale it up into that scientific notation. So I'm identifying, hey, here's my decimal place. I'm going to start with that. And I need my number in between 1 and 10. So to accomplish that, I'm going to move my decimal over 1, 2, 3, 4, 5, and 6. Notice now I end up with 5.06. Well, that's in between. 5.06 is in between 1 and 10. Okay. And I had to move that decimal over 1, 2, 3, 4, 5, 6 times to accomplish that. So I have, for my scientific notation, times 10. And again, since I started with a really small number and made it into that scientific notation form where it's bigger, I have that -6. Again, I started with something small. That's why I have that negative there. So you can almost think like, hey, small equals negative exponent. So if you start with something small, you're going to have that negative exponent. For F, starting with something absolutely huge, 83 looks like billion, 40 million. So that's obviously a very, very huge number, very large. This is a large number to start with. So as a result, I know my exponent is going to be positive in the end. And what I want to do is identify where is my decimal. Well, it's at the very, very end of my number. And now I'm going to shift that decimal over to get that number in between 1 and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And I need to go one more, 10, to get that in between the 1 and 10. So I end up then with 8.304. And all the other numbers beyond that are just zeros. So I don't even have to keep going. I can just leave it as that decimal place. And again, we had to move that decimal over 10 times. So this is now why we have our scientific notation always times 10. And our exponent is that positive 10th power. Next up, we have 46.2. Now, this isn't really a super massive number, but it is a larger number than 10. So you would consider this one as kind of like a large number because it's more than 10. And we want to get our number in between always 1 and 10. So we're identifying where our decimal is. There it is, 46.2. And I want this number in between 1 and 10. So I'm going to have to move this decimal over, it looks like in this case now, 1 place. And so when I do that, I end up with 4.62. So we're rewriting all those values, all those numbers, times 10 always for scientific notation. And our exponent is, again, we started with a large number, so we have a positive exponent. In this case, we moved that decimal over 1 time, positive ones. Next, moving on to H. So we have the number 3. Well, 3 is really the same thing as saying 3.0. Right? 3.0 is the same as 3. And so if we're trying to convert this into scientific notation, it looks like our number 3 is already in between 1 and 10. So we end up then for the scientific notation 3.0. And scientific notation always has that times 10. Well, our start 3 was already in between 1 and 10. And so we really didn't need to move our decimal at all on this one because it was already, again, in between 1 and 10. And so that's why, since we didn't even move our decimal, it would be to the 0th power. And that's actually our scientific notation. That was the last one in that definition that we saw earlier. So anytime you don't move your decimal, it's 0 for that exponent. All right, next one up, we have 670,400. Well, this is obviously, yes, a very large number. And we want to first identify where our decimal place is. It is right here at the end. And we need this number in between 1 and 10 always. So when we do that, we end up with moving it 1, 2, 3, 4, 5. Now I have my 6.7, which is in between 1 and 10. And then I also have my other numbers 0, 4. Don't need to include those extra zeros later on. Times 10 for scientific notation always. And again, it looks like we moved it over 2, 3, 4, 5 places. So again, starting with a very large number, bringing it down to scientific notation, we have a positive exponent there. And we moved it 5 times. For J, 0.05 is a pretty small number. It's pretty close to 0. It's a decimal, pretty close to 0. And what we want to do is get this number in between, as always, 1 and 10. Well, here's our decimal place. Looks like we're going to have to move it over. That would not quite get me in between 1 and 10. 0.5 is smaller than 1. You know, always between 1 and 10. So I'm going to have to go one more time. And I get the number 5. So I have 5.0. 5 is the same as 5.0 times 10. And it looks like I had to move that 2 places, that decimal 2 places. And again, I started with a really small number, which is going to equal a negative exponent. In this case, -2. Again, you're really always looking at what did you start with? And if it's a small number to start with, and you're bringing it to scientific notation, you have a negative exponent. If you have a large number, like that one, F, if you start with that, then you're going to have a positive exponent. What I would love for you guys to do now is to go ahead and please pause the video and try these triads, these 1 through 6. So I do want you to actually, yes, pause the video, give them a shot, get some reps in, and try them out. And then in a moment, we'll come back together, and then we'll go through them one by one. All right, hopefully you've had an opportunity to try each one at this point. First, we have 50,000. So this is considered a large number, and our decimal place is at the end. And so when we're converting this into scientific notation, we would have to move this over 1, 2, 3, and now my number is in between 1 and 10. So I have 5.0, and it looks like I moved that decimal over 5 times. Actually, we'll give ourselves some space. So 5.0 times 10. And again, we moved that decimal place 5 places. And since it was a large number to begin with, we have a positive 5 there. As we move on to number 2, beginning with 25 million. Well, that's obviously a very large number. And we know that that's going to give us a positive exponent. Identifying where is our decimal? Well, here it is. It's at the end. And so we're going to move it over 1, 2, 3, 4, 5, 6, 7. Total of 7 places. And so for this scientific notation, we end up with 2.5. Well, that number is in between 1 and 10, like it should be, times 10 for scientific notation, raised to the positive 7th exponent. And there is number 2. For number 3, we have 683. Again, our decimal is here at the end, and we need our value not at 683, but between 1 and 10. So it looks like we're going to have to move this decimal over 1. That would be at 68. That's not between 1 and 10 yet. But if I move it over one more time at 6.83, my number is now in between 1 and 10. Times 10. And again, we began with a large number, so we know we're going to get a positive exponent. And it looks like we moved it over twice, so we end up with a positive 2 there. For number 4, we're beginning with 0.005. Well, that's pretty small. This is a small number. And we need it to be in between 1 and 5, or 1 and 10. So identifying, here's my decimal. I'm going to move it over 1, 2. I need to go another third time to get this value in between 1 and 10. So I end up with 5.0 times 10. And again, I started with a small number. This is going to be giving me a negative exponent. So we end up then with negative, however many times you ended up moving the decimal. In this case, we did 3. So you should have had 5.0 times 10 to the negative third. For number 5, super similar, you just have a much larger decimal. So 0.00000033, that is an incredibly small number, tiny. So we know we're going to get a negative exponent. And so the question is, well, how many times do we have to move it over? Looks like 1, 2, 3, 4, 5, 6, 7 places. So we get 3.3 times 10. And again, we moved it 7 times in the negative exponent. Because again, we started with that small number. For question number 6, again, super similar, starting off with a small number. Got to get this value in between 1 and 10. So we're going to move it over 1, 2, 3. Got to move it over 4 times. And when we do that, we end up with 5.06 times 10 raised to the, again, it started with a small number, so that's why we have a negative. We move the decimal place over 4 times. So there's our scientific notation. And for the record, for all of these, if you're ever uncertain, you're like, hey, did I go the right way? Is my exponent correct? You can always check these. So for example, for like number 3, we ended up with 6.83 times 2 or times 10 to the second power. But we got a lot of practice with this yesterday, where you had to, when it was in scientific notation and you had to go to standard, you would move that decimal over however many times in that direction. So because it was positive 2, we would have to move that then 2 in this direction, and then you get 683. Well, that was our original, right? Similarly with question number 6, if you're like, hey, did I get my sign correct or not? I have negative 4 there. That means I have to go in this direction 4 times. And then I throw in those zeros. Lo and behold, I get my original. So if you're ever uncertain, you can actually check and verify what you have. right. So these were the eukaryotes 1 through 6. Go ahead, feel free to pause the video if you have any questions at all. All right, now looking at example 4, the table shows when the last 3 geological eras began. And our goal is to order these from the earliest to the most recent. So it looks like this Paleozoic period was 5.42 years ago. And there's a couple of ways we can do it. Personally, I would probably make this into standard form. And so then I would just compare numbers, but we'll see both routes too. So then that way you can kind of choose which one you prefer. So for this guy, we have times 10 raised to the 8th power. We would then move this decimal over 8 times in the right direction because it's a positive 8. So 1, 2, 3, 4, 5, 6, 7, 8. And then what I would do is include those zeros where they belong. And so I ended up then with 542. And then looks like 6 zeros afterwards. So 542 million years ago was that period. For the Cenozoic, we have 6.55 times 10 to the 7th. And very similarly, all you're going to do is just move that decimal over 7 times. So 1, 2, 3, 4, 5, 6, 7. This is really more of that like part 1 approach that we saw yesterday. And then we throw in our zeros. And so then you end up with 6, 5, 5. And then it looks like a total of 5 zeros following it. So 65,500,000 years ago. And then finally, the Mesozoic. So 2.51 times 10 raised to the 8th power. So we would be moving this decimal over 8 times. So 1, 2, 3, 4, 5, 6, 7, 8. And then we fill in our zeros. So we end up with 2, 5, 1. And then looks like 6 zeros afterwards. 3, 4, 5, 6. So 251 million years ago for the Mesozoic. All right. So from the earliest, sorry about that. Sometimes when the, like if it reaches like a certain point on the PDF file, it'll suddenly jump to the front page. And then it unfortunately like deletes the most recent writings. So if you need to, just go ahead, rewind to like about 30 seconds ago and you should see that work. But these are the answers that we just ended up with. And it looks like the Paleozoic is the oldest one. It's at that 542 million. So this is the oldest. This is the earliest. So we'll say the order, I guess, would be like, we'll just say earliest. Or like this would have came first is the Paleozoic. And then the Mesozoic was 251 million years ago. So that would kind of be placed at number 2 in time. And then the Cenozoic was only 65 million years go. So that would kind of be ranked as the most recent. So more recent. So that is one way that you can do it. Just creating them in standard form and then comparing those numbers just as they are. Okay. I'll say that that is also one of the safer moves. The other way, though, is looking at your actual scientific notation. And this is where it's pretty handy, where especially if you're really good with the numbers and you can kind of see what's going on with the integers as well as the exponents, you can kind of get these things much faster. Okay. So notice the exponents are going to play a much larger role than the integers. Okay. So like, for example, if I have 8 as an exponent and then I have 7, well, 8 is obviously bigger than 7. So this would be more in terms of like an overall size because of that exponent being larger. Now, what happens when you see that they're exactly the same? So for example, in the Paleozoic and the Mesozoic, they're both sharing that exponent 8. Now, this is where the integers come into play. So you want to look at your 5 versus your 2. Well, 5 is obviously bigger than 2. And so that's how you know in the end it's going to be more because it's a bigger integer. So again, you always want to start with kind of like the order would be check out your exponents. So you always want to start with look at your exponents, see which ones are the biggest versus the smallest. And then kind of like step 2 is if you have the same, you want to compare your integers. So that kind of like that first number in front of the decimal. Okay. And so that's actually, again, really efficient, fast way to do it. So in just looking at these, Paleozoic has a high exponent, like 8. So does Mesozoic. So in my head, I'm thinking these are some of the oldest ones because they have the bigger exponent. But since they're the same, I'm going to look at the integers, 5 versus 2. 5 is certainly bigger, so that's why it's the oldest. But then when I look at the Cenozoic, well, that exponent is defeated by the 8. And so that's why Mesozoic is just bigger. It's older. So again, it boils down to exponents. If they have the same exponent, then compare your integers. And really, guys, at the end of the day, it's those exponents that make things really, really big or really, really small. Okay. That's why we mainly hone in on that first. Now, the Tyrannosaurus Rex lived 7.0 times 10 to the 7th years ago. Consider the areas from example 4 and which era did the T-Rex live in. So if I have 7.0 times 10 to the 7th, I've got 7.0 times 10 raised to the 7th power. My goal is to try and figure out, well, how many times am I going to move that decimal over? You could even probably just look at it and say, hey, it's in this one. And so this is a prime example where we just say, hey, look, using those scientific notation and dates and years ago, you can reasonably predict. Go ahead. You could probably take a moment, try and guess which one. And if you said Cenozoic, you are absolutely right because, again, it's that sharing of the same exponent there. They were in that same kind of time period. Just to kind of help illustrate it, if we were to make this into a standard form, I can move that decimal over 7 times. So 1, 2, 3, 4, 5, 6, 7. Fill in these zeros. And so once I'm all done, I end up with 7, 0. So, 70 million years. So again, that's the standard form approach, which is pretty close to our 65 million years. Okay. But typically now at this point, most of us are going to begin to look at those exponents and just recognize, hey, they happen to be exactly the same, times 10 to the 7th, times 10 to the 7th. And so this really helps scientists just kind of place certain items in certain dates and times. All right. Next, what we have here, guys, is a scientific notation and standard notation. And we have two completely separate columns. This is an awesome practice where you're kind of going in between the two of them and really going back and forth between the two of them. So if I have 7.8 times 10 raised to the 10th power, currently that is in scientific notation. What I want to do is make this into standard notation. I just want the number itself. So kind of like with part 1, I'm going to move this decimal over. It looks like 10 places in the positive right direction. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, anywhere that there was that little bump, we throw in the zeros. Notice I have my positive exponent, 10, positive 10 for the exponent. And I'm getting a really large number here. I'm getting 7, 2, 8, and then, oh man, probably what, 8 zeros? Yep, 8 zeros after that following it. So for standard notation, 1, 2, 3, 4, 5, 6, 7, 8. And then again, the commas. So that scientific notation boiled down to 72,800,000,000 as the standard notation. Again, positive exponent, really big positive number, like a really big number. For the next scientific notation, again, we have a negative exponent. So we know that we have to have a really small number then. It's close to 0. So we're going to take our decimal and shift it over 3 places in the left direction. So that's 1, 2, 3. I have my decimal. And I end up then with my small number 0.003409. Again, that number though is really close to 0, which makes sense with my negative exponent. We'll do another one in terms of like standard form or standard notation, getting it into scientific. That's a little bit more of what we highlighted today. So we end up with this small number, really, really close to 0. I need to move that decimal over 1, 2, 3, 4, 5, 6 places. And when I do that, I have 5.81 times 10. And because I started with a really small number, I end up with a negative exponent. So this would be times 10 raised to the negative 6 times that I moved that decimal. Again, this number is in between 1 and 10 times 10 raised to that negative 6. So that would be our scientific notation. So we had 5.81 times 10 raised to the negative 6th. What I would love for you guys to do is pause the video and try out these next questions. Again, you're kind of going from either scientific notation into standard or from standard into scientific notation. Again, guys, really, yes, pause the video, try them out, and see how you do. All right, hopefully you guys have had an opportunity to try those. Again, when it's 9.1 times 10 to the fourth, we are going to shift that decimal over 4 places to the right because that's a positive 4 exponent. So again, 1, 2, 3, 4. We throw those zeros in there. And so we end up then with 91,000. For our next guy, we have, looks like 9,081,000,000. And we're trying to get that scientific notation. So we're identifying where's our decimal place. Here it is at the end. And I need to get my number in between 1 and 10. So we end up doing then 1, 2, 3, 4, 5, 6, 7, 8, 9 places. Again, moved it over 9. And so we ended up then with 9.081. Don't need the other zeros, that's fine. Times 10 raised to the 9th power. Again, it's a positive 9 because I began with a really big number. Now, after having seen those two, if you need to try some of these again, go ahead, pause the video, and maybe retry a couple if you feel that you need to. Again, if you feel like, hey, now I'm kind of getting the swing of it, I would rather you do it correctly. All right, now that you guys have hopefully had a chance to, again, if you already felt comfortable before, great. If you had the chance to redo some of them, fantastic. Again, it's all about doing it correctly in the end, because that's what's going to pay off on the quizzes and tests. So on this one, 27.58, that is bigger than 10. And we're trying to get this into scientific notation. So we're going to have to move that decimal over 1 place. Now my number is in between that 1 and 10. So I end up then with 2.758 times 10. And this 27.58, that was considered kind of like a large number. It was more than 10. And so that's why we're going to have a positive 1 exponent there because we only moved the decimal place once. Next up, we're starting off in a scientific notation, trying to get it to standard. So if I have 1.54 times 10 to the -5th, what I'm going to do is move that decimal place over 5 times to the left because it's a negative exponent. So 1, 2, 3, 4, 5. And then we throw in the zeros. And so when we're all done, we end up with 0.0000154. And that would be our standard form. Notice, really, really small number, negative exponent, they go hand in hand. Okay, that negative exponent with our small number in the end. Next guy up, 5.31. Well, our integer is actually already in between, or I'm sorry, our value for standard form is already in between 1 and 10. And so we really don't need to change this one. It's just going to remain 5.31 times 10. And I didn't have to move my decimal at all in the positive or negative direction. So that's why it's to the 0th. For our next guy, 6 times 10 to the 5th. It's in scientific notation, trying to get it to standard. Again, we're going to identify where our decimal is. Anytime you have an integer like this, we know that the decimal is at the end. And we're going to move it 5 times in that positive direction because we have positive 5. So 1, 2, 3, 4, 5. And then again, where we see those little bumps, we throw zeros in them. So then we're looking at 600,000. For this guy, 0.007009. That's a really tiny number. I'm trying to get this into scientific notation. Well, I'm going to need to move this decimal over 1, 2, 3 places to get this number in between 1 and 10. So we end up with 7.009. You can't forget about that because that 9 is a number. It's part of our standard form number. Times 10 raised to the, we had to move this 3 times, but since it was a really small number to begin with, we have that negative there. Okay. And so a lot of the times the big confusion is like, well, which way do I move the decimal? And especially like the signs, like when is it negative versus positive? Really, guys, just think about what you're starting with. Is it a small number or a big number? Okay. If you do that, that pretty much tells you what sign you're going to have. So again, another great prime example of that. We have a number pretty darn small, close to 0. So this is going to be negative exponent when it's all done. Again, we have to move this decimal over. Got to get it in between 1 and 10 for scientific notation. So 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Now currently, that's in between 1 and 10. So we have 4.0 times 10 raised to the negative 9th power because we moved it over 9 times. Okay. For me, if you just put 4 times 10 to the negative 9, I would take that, but the safer move is 4.0. Next up, we have 8.4 times 10 to the negative 6th. Again, negative exponent there, trying to get this in standard form. Because it's a negative exponent, we're going to move it left, and it's going to become a really small number. So 1, 2, 3, 4, 5, 6. Now we throw in our zeros for those bumps. And there's our standard form. So we end up then with 0.00000084 when it's all done. For 6.02 times 10 to the 8th, it's a positive 8 for this exponent. So this is now where we move it to the right. It's going to create a big number, a really, really big number, because it's a positive exponent. So again, 1. We'll do red. Keep it consistent. 1, 2, 3, 4, 5, 6, 7, 8. And then again, we throw in those zeros where they belong. And so we end up then with 602. And then looks like 6 zeros afterwards. So 602 million. Standard form number, 56,090,000. Got to try and get in scientific notation. So this is obviously a very large number to start with, which is going to give us a positive exponent. And we're starting off over here at the very end for our decimal. And we're going to move it over. Looks like 1, 2, 3, 4, 5, 6, 7 places. And then we end up with 5.609. Yes, you need to include all those numbers. And then times 10 raised to the positive 7th power, because we moved it 7 times. And lastly, 4 times 10 to the 0th power. Well, the standard form for that is taking our decimal, moving it 0 times, like 0 places left or right, so you just get the number 4. That would be it. Okay. So just a quick recap. Those are our different answers for this scientific notation and standard notation. You guys are going to need to know how to be able to go back and forth between the two. So, this sheet right here is a very excellent one. I will say some students get mixed up on what is what, like which way do I need to go? If you need to reference this one though, please do it. If you need a blank copy of it, please do it. Try the practice. It's very, I don't want to say it's easy to get them mixed up, but you might think, hey, I'm in standard notation, I need to get to scientific, where it might be the other way around. Or be careful which way you move your decimals. Okay. So again, standard notation is pretty much just your number. If it's a really small one to start, like this guy, you're going to have a negative exponent always. And it looks like on this guy, we moved it, 6 times? 1, 2, 3, 4, 5. Yeah, 6 times. 6 times there. And that would become then that negative 6 exponent. For scientific notation, always, always, always has to be in between 1 and 10. Always, no matter what, between 1 and 10 for scientific. Okay. So again, try hard on your guys' practice. This will show up on your guys' quiz and test. So make sure you guys know how to be able to go back and forth between each type. All right. But again, though, that is our 4.12 part 2 set of notes.